All right, then we can go ahead and get started. Our fourth is Matt Bullimore talking about generalized symmetries and vortices. Take it away, Matt.
Okay, thank you. Hello, everybody. And thank you for the invitation to speak. And I appreciate the chance to speak online. Sorry that I couldn't be there. I'm afraid my young kids are keeping me firmly grounded in the UK. So I'd like to tell you about a topic that I've been interested in the last couple of years, which are called generalized symmetries, which are kind of generalized notions of symmetry in quantum field theory, and some interactions of that topic with hopefully topics that are of interest to people at this workshop. So yeah, please do feel free to stop me and ask questions. I'm very happy to explain from different perspectives, or I have a whiteboard behind me as well, which I could use. All right, I'll keep an eye on the chat as well in case anyone wants to ask questions there. All right. So let me first give an introduction and some motivation and what I'd like to talk about. So the topic is about generalized notions of symmetry in quantum field theory. And in the last, 10 years, but accelerating, and specifically in the last couple of years, there's been quite a big generalization of what we mean by symmetry in quantum field theory. So one way to phrase it is the following. We normally think about symmetries as groups that act in some way on a field theory. And ordinary symmetries, which are described by groups, they might be continuous or discrete, they act on local operators in your theory, so point-like operators. And the local operators will transform in representations of that symmetry. And moreover, the symmetry might reflect in lots of other means. For example, if there's a moduli space, it might act on the moduli space in some way. Well, okay, generalized symmetries, one way to describe what they do is that they act in an interesting way, not just on local operators, but also on extended operators. So maybe operators that are supported not just on points, but on lines or surfaces, or perhaps local operators attached to lines or lines attached to surfaces. And all these things, all these new types of symmetries should be important for quantum field theory. And they have a kind of categorical nature to them. So the symmetries can form what's called higher groups or N groups. And moreover, the symmetries, although I won't talk about it today, the symmetries can even be non-invertible. So they're not even group-like in any meaningful sense. They're just described by certain higher categories. But nevertheless, they behave, for all intents and purposes, as symmetries do in quantum field theory, and they can be used in exactly the same ways. Okay, so this is this paradigm of categorical symmetry. Well, there's been a lot of excitement specifically about non-invertible symmetries in the last year or so, but today I want to talk about ordinary group-like things or higher group-like things. Okay. So I particularly want to talk about how this notion of symmetry interacts with geometry. And in the context of quantum field theory, that's going to be the geometry of moduli spaces that arise in quantum field theory, and specifically supersymmetric field theory. So you might have a quantum field theory with some moduli space of vacua, and perhaps supersymmetry or something else endows it with some geometric structure. And ordinarily, the way symmetries work is that they will act by automorphisms of that structure. So they might act by isometries of your moduli space. Okay. And so the idea is that when we consider these higher form or these higher symmetries, higher form symmetries, higher groups, we're going to need to pass to a more refined notion of geometry of moduli space. And in particular, those symmetries are captured by studying moduli stacks. And this is something that physicists should care about very much. It's one way to say what it is it keeps track of things like unbroken discrete gauge symmetry. And so here's a kind of cartoon picture of what a stack might look like. And so one way to think about it is that there's an underlying moduli space that they call X sub 0. And that's the kind of ordinary space you might think of. Maybe you want to think about it as a Kähler manifold or a hyperkähler manifold, depending on the context. Or maybe you want to think about it algebraically as a variety, depending on what context you want to live in. And ordinary symmetries in quantum field theory, they will act by isometries of that structure. So they will act on the base here. On the other hand, you can think about the whole moduli stack that I'll call X as a kind of fibration, where the fibers, well, whatever the heck they are, there's something that keeps track of the fact that you might have discrete unbroken gauge symmetry if you sit at a point on that moduli space. Or more generally, you might sit at a point on the moduli space, and the theory is not quite trivial in the infrared, but there's a leftover TQFT, topological field theory. And the fiber is something that captures that. And the idea is that these higher symmetries will act on the fibers in such the way that everything combines together, and you have a nice picture where all of the symmetries you have in your theory, including high form symmetries, act in a nice way on this stacky moduli space. And this can really encode a lot of structure. It can encode not just symmetries, but also their 't Hooft anomalies. And in a way, it's capturing spontaneous symmetry breaking of these symmetries. Okay. So that's a very rough cartoon picture of the type of structure that I want to think about. And so today I want to try to explain some connection of those ideas with the topics in this workshop. And so in particular, the type of moduli spaces I want to look at are going to be something like a Higgs branch moduli space for some gauge theory, three-dimensional gauge theory. And we're going to be studying things like vortices in that gauge theory or quasi-maps into this target space, this stack. And so you might hope that the symmetries, the enlarged symmetries, will play some role in constructions associated to that. Okay, so I'm going to talk about supersymmetric field theory. So in 3 dimensions with n equals to 2 supersymmetry. And the talk will be roughly in 3 parts. So the first part, I just want to give a bit of background about symmetries in quantum field theory, higher form symmetries, higher group symmetries, and specifically in 3D gauge theory. And I should say I'm going to focus very much on a specific example today all the way through. And then in the second part, I want to talk about how those symmetries are manifested in, or how we can think about moduli stacks for those gauge theories, and how the symmetries are manifested by automorphisms of that stack. And so that this picture involving moduli stacks in gauge theory is something that we've been developing with Lakshya Bhardwaj and Andrea, who spoke just before me, and Sakura, Schaefer-Nemecki. And then in part 3, I'd like to talk about some connections to quantum K theory, or really quasi-map K theory of Deligne-Mumford stacks, and try to put forward the idea that these higher symmetries should play a role there, and there should be some higher notion of equivariance in this theory. And that's something I've been thinking about with Luca Cassia, who's a postdoc in Durham. All right, so I'm going to move on to part 1, which is gauge theory. So maybe I'll just pause and see if there are any questions. All right, I can see a thumbs up, so I'll keep going. Okay, so I want to talk about a gauge theory. And as I said, I'm going to focus on a very specific example all the way through. hopefully this will give the idea. And then if there are any questions about general structures, you're very welcome to ask me about that. So I'm going to stick with an abelian gauge theory. So this is like a gauge linear sigma model. The gauge group is just U1, so it's rank 1. And I want to have n chiral multiplets. I'll call them phi 1 up to phi n. And so perhaps ordinarily I would give them charge 1. That would maybe be a standard thing to do, but I'm going to be interested today in taking the charge of these chiral multiplets, their weight under the action of U1 to be greater than 1. So some integer q, which is 1 or greater. Okay, so this is the same kind of data that labels a GLSM in 2 dimensions that you might study when you want to study something like quantum cohomology of projective spaces. But in 3 dimensions, there's an extra ingredient you have to worry about, which is the Chern-Simons level. And that leads to lots of interesting new phenomena that are quite different to 2 dimensions. And I'm going to choose a specific level for today. It doesn't really matter what it is, but this level is what I'm going to call critical. And so I missed Andrea's talk this morning, so I'm not sure how much he said, but there's kind of a window of Chern-Simons levels where nice things happen. Outside of that window, you get extra states that spoil the connection to geometry. So and this critical level is the level that sits kind of right on the edge of that window. It's the level that's most interesting it's the level that's most close to what you would do in 2 dimensions. It's also the level where you have interesting effects like mirror symmetry, 3-dimensional mirror symmetry. But the most important thing for me today is that what it means is that the charges of all of the matter that I have in the theory, including the monopole operators, which is again a new feature of 3 dimensions, the charges of all the objects, all the local objects in the theory are all multiples of n. So that's already true for the, okay. So indeed, the gauge charges of all the monopoles are multiples of n. All right, so let me talk about some symmetries in this theory. So I'll start out with some standard ones, and then I'll move on to the more non-standard ones. So the first are ordinary symmetries, or what I'm going to call zero-form symmetries. So they're groups. They don't have to be abelian, but they can be abelian. They can be continuous or discrete. And a fundamental role for this talk will be what's called the topological symmetry. And so this is a symmetry that you have in any abelian gauge theory. And so here the rank is 1, so the symmetry group is just U1. The charges are integers, and it just measures magnetic flux. So for example, if you have a monopole operator, Tm, that's an operator which by definition creates a non-trivial magnetic flux through a 2-sphere that links it. Then if it creates magnetic flux M, then we say that that operator has charge under this symmetry M. And in a way, this is the 3-dimensional version of a theta angle in 2D. A theta angle you would call a -1 form symmetry. But instead of something you add to the action, it's now a symmetry. Okay. So in addition to that, there's a symmetry that acts by rotating the chiral multiplets. There were n chiral multiplets, and they transform in the fundamental representation of the Lie algebra SUN. But if we want to know about what the gauge group is, we should really ask ourselves what acts faithfully on the genuine local operator content in the theory. And the claim is that that group is PSUN. It's the global form PSUN. So here it's really important for me in this story and in all of this connections to generalized symmetries that we really pay careful attention to the global form of the symmetry groups that we have. It's crucial for these generalized symmetries for 't Hooft anomalies for all sorts of things. Okay, so why is it PSUN? Well, basically, if you look at the genuine local operators, all of the gauge invariant stuff you have in the theory, basically they all transform in things you can build out of the adjoint representation. So for example, you might take a complex scalar phi times a complex, the conjugation of a scalar phi times a scalar. So this will be gauge invariant, and it transforms in the adjoint representation. And then maybe you can get other things involving monopole operators that are not gauge invariant by dressing them with charged matter. Here it's really important that the charge, as of all the monopoles, are n. This is crucial for this statement. If I changed the Chern-Simons level, this would not have been true. More interesting things would happen. But anyway, all of the local operators you have in the theory, the genuine local operators, they're all in the adjoint or powers of the adjoint. And so the symmetry group that acts faithfully is PSUN, the projectivized group. Okay. But there can be more. All right, so we had some zero form symmetries. There's a topological symmetry. There's this PSUN symmetry. Maybe it's useful to say that this factorization into two pieces only happened because of this particular choice of Chern-Simons level. Otherwise, these things tend to get mixed up. But here we have a clean separation. But there are more symmetries in the game. In particular, there can be what's called one-form symmetries. And moreover, the zero-form symmetries that I've described and the one-form symmetries can combine into a two-group. And all of those things can have 't Hooft anomalies, and they do. Even in very simple theories like this. So what is this one-form symmetry about? What's it capturing? Well, the essence of it is capturing the fact that line operators in the theory can't end. So that's the basic statement that you have a one-form symmetry. There are some line operators in your theory that can't end. And then those operators can be charged under a one-form symmetry. This is why it's higher, because the things that are charged under it are lines now, not local operators. And there can be more interesting structure that connects the two things. So it might be that some of the line operators can't end, but others that do end, they may transform, the operators on which they end may actually transform in representations of an extension of the flavor group that are not representations of the flavor group. And that in part captures this higher two-group structure that you might have. So let me give a specific example of that. So we've got our gauge theory. So the nicest type of line operators we have are Wilson lines. So it's a U1 gauge theory. So the Wilson lines just have a charge, n, which is an integer. And the basic statement is that because all of the matter fields have charge q, then the Wilson lines can't end. Well, they'd have charges which is a multiple of q. That was the charge of the chiral multiplets. The Wilson lines can't end unless their charge is a multiple of q. There's just nothing for them to end on. And so what this means is that you have a ZQ. In that case, we say that you have a ZQ one-form symmetry, a discrete one-form symmetry. And the charge of the Wilson line under that symmetry is the charge of the Wilson line, mod Q. But more interesting things are true, not just this. If you look at a Wilson line that can end, so if n is a multiple of Q, you have to look what it does end on. And it might be that the operators that it ends on transform in representations of an extension of the flavor group. And so that happens in this case. In particular, you will find that the operators that it ends on transforms in representations of SUN that are not representations of PSUN, typically, unless it happens that the charge of the Wilson line is in fact a multiple of Q times big N, the number of chiral multiplets. So here's a kind of picture. So you've got your Wilson lines increasing. The Wilson line of charge 1 can't end, 2 can't end until you get to Q, charge Q, and then suddenly it can end on the chiral multiplets because they have charge Q. But these chiral multiplets are going to transform in the fundamental of SUN. And that's a representation of SUN that doesn't lift to a representation of PSUN. So you have this type of phenomena here where you have to enlarge the flavor symmetry a bit when you're studying things that sit at the end of lines. Okay. All right, so the two-group structure kind of that you get depends a little bit on these numbers Q and N and how they interact, and in particular whether they're co-prime or not. So let me try to give you a flavor of what the full symmetry structure is. So there can be a two-group symmetry in this theory. So the zero form part is PSUN, just acts on the chiral multiplets. The one form part is ZQ. The charged objects there are the Wilson lines, and Q is the charge mod Q. But these symmetries can form kind of like an extension. It's a bit like an extension, but you're extending by something in one higher degree. So instead of H2, you need a H3. And this extra data is called Postnikov data for the two group. And whether or not this two group is split, or whether the Postnikov data is non-trivial, depends a bit on Q and N. In particular, it depends on this short exact sequence. So there's a short exact sequence here that arises by studying the spectrum of Wilson lines and what they can end on. And basically, if the sequence splits, then the two group is split. And if the sequence doesn't split, then this two group is an extension. And that depends very much on whether Q and N are co-prime. So in order to get an interesting two group, we need to have that they have a common denominator that's greater than 1. So for example, two chirals of charge 2 would be good enough to get an interesting two group.
Just a quick technical question. So the Postnikov class, you write it as an element of H3 of the classifying space. In other expositions of two groups, one sees H3 of in group cohomology, and these are not the same when.
Yeah, I mean, if the zero form group is discrete, then those things are going to be the same. In the case that it's
why is
in the case that it's continuous, this will be the correct thing to do.
Okay.
I mean, you have to say what you mean by group cohomology if the group is continuous, I think. And I mean, having said that, this group here is
that class comes up. Yeah. So that comes up because there's a lack of associativity in the zero form.
Yeah, that's one way of framing it. Yes. Yeah.
Sorry, the batteries are flaking out.
No problem. Yeah.
So that lack of associativity looked like it was defining a class and group cohomology.
Yeah, and if everything is discrete, then that all follows through.
So you're saying like this is the right generalization of that for a continuous group.
Yeah. It can sometimes be helpful to think about it in terms of the background fields that you turn on for these symmetries. And if you do it in that way, it kind of makes clear that this is the right generalization as well. Okay. Shall I?
Thanks. Thanks a lot.
Okay. All right. But yeah, I mean, let me emphasize that this is nothing too fancy. I mean, this is a discrete group ultimately here. And, you know, this is just a number, really, a discrete thing. And it can be determined. All right. So I'd like to mention another way to think about the symmetries, which is going to be useful in what I want to say, which is to talk about what's called the structure group of a gauge theory. So I call that S. So what is the structure group? Well, the structure group is basically the most general combination of gauge and flavor symmetries for which I can consistently couple the theory to bundles. So I can turn on bundles in space-time for S. It's the largest group for which I can do so. And in this case, it takes the following form. So the numerator, it's a combination of the gauge, which is U1, and the flavor symmetry, but they're mixed up in a slightly interesting way. And all sorts of problems to do with the symmetries and 't Hooft anomalies can be framed in this language. So you take U1, which is the gauge group, you take SUN, which is the largest cover of the flavor group, and then you quotient by a central subgroup, which in this case is ZQN. And it's generated by this element here. So it acts just by a phase, a QN root of unity on U1, and then simultaneously by an action of the center of SUN. Okay. But this is the most it's a very natural group. It's the most general group that you can turn on bundles for, or you can couple the theory to. And the symmetries can be recovered in a nice way from this structure group. So in particular, to find the zero form symmetry, what you do is you basically, you look at the denominator here. It's an element of the center, and you basically project onto the SUN factor and take a quotient. And that just, in this case, that just quotients SUN by, this is a typo here, sorry about that, that should be ZN. Quotients SUN by its center, and that gives you PSUN, which is the true flavor group in this case. On the other hand, the one form symmetry you get by taking the quotient here and just intersecting with U1, or rather the center, but in this case just U1, and that's ZQ, that's the one form symmetry. But in this way of framing it, it's natural that you get a short exact sequence from these two groups like this. And so you can basically recover all of the structure that you'd like from this structure group. Okay. All right, so now I want to translate some of this into geometry. So maybe I'll just pause here and see if there are some more questions, in case it takes a while to get the microphone over. All right, good to go. Okay. So I want to translate some of this into geometry now. And the idea is we're going to go to a regime where the gauge theory flows to a sigma model, or what's roughly a sigma model. So what's the idea? We introduce an FI parameter. So we force the theory into a regime where it flows to a sigma model, except it's not quite a sigma model. And that's the crucial point. So basically, it's a fairly standard thing that when you introduce a real FI in this theory, it's going to flow to a sigma model onto projective space, CPn-1, which is parameterized by the expectation values of the scalar fields. But there's an important point here, is that if you sit at any point on that moduli space, if you give any vacuum expectation value to the chiral fields, there's always going to be an unbroken ZQ gauge symmetry, because all of the fields have charge Q. And so you need some geometric structure that captures that. I mean, even physically, you don't really quite flow to a sigma model. What you really do is you flow to a sigma model coupled to a discrete gauge theory. So in particular, you have to couple the theory to some discrete gauge fields for ZQ. That's A. And then you give a particular coupling of the sigma model, a topological coupling of the sigma model to these discrete gauge fields, which takes the following form. In particular, it's linear in the gauge field, and the coefficient is some class on the target space here that you pull back via the map in the sigma model. Okay. And so the idea is that coupling to these discrete gauge fields reflects.
Sorry, Matt. I have another stupid question.
Please, yeah.
What's a ZQ gauge field?
Indeed, right. You just think of it as a class on space-time. It's probably the best for now. That's probably the best way. So it's a H1 on space-time with coefficients in ZQ, and you can think about that however you like.
Pulled back from H1 in group cohomology of ZQ.
If you like, yeah, yeah. So if you like, you could think about it as a
Makes
map.
sense. Thanks.
If you want, you could think about it as a map from space-time into BZQ up to homotopy. All right. But the main point is
that a question, if possible.
Yeah.
How do you come up with the class C that you have here?
Yeah, I mean, on the one hand, it's the only coupling that you could write down for some class C that's linear in the gauge field. And then, of course, you have to do a computation to check what the class is in the example.
Yeah, so I was curious as to what is the computation you have to do to find what C is.
Yeah, basically you follow through the GLSM construction. So you really try to flow to a sigma model. You solve for the fields, you substitute back in and see what terms you get in the action when you do that. And if you do that very carefully, you will end up spitting out something like this. And C is non-trivial. So this group here is basically ZQ. And if you think of that additively, the class is -1. It's something you can check. Okay. So yeah, it's a computation. It's one that I'm not doing, but you have to take my word that it's non-trivial and it's -1. Okay. All right. So I want to think about, it would be nice if we could think about,
Matt.
Yeah.
Matt. Sorry, just I know you know this already, but also just for like the mathematicians in the room, like this is the class that classifies like ZQ gerbs over p to the n -1.
Yeah.
So you just take the quotient stack, map it to your course quotient, which is p to the n -1, and then just ask like what gerb is it?
Yeah, that's my next slide. Thanks. Thanks. All right, so it'll be nice indeed. It would be very nice if we had a more pure geometric picture. So what is really going on? Well, another way to say it, as Justin pointed out, is that you think of it as a sigma model whose target space is the weighted projective stack. So instead of taking the GIT quotient, you take the stacky GIT quotient. And this is a weighted projective space. So I write it like this. And indeed, in this case, as Justin said, it's a stacky space, but the automorphisms are ZQ everywhere. And so it's a gerb in this case. And so again, the way to think about this is that it's a bit like a fibration. There's a morphism to the underlying coarse moduli space, which is ordinary complex projective space, where the fibers of that morphism, BZQ, they capture the unbroken ZQ gauge symmetry. And indeed, the stack is a gerb in this case. Fibers are roughly the same everywhere. And there's a non-trivial class attached to that gerb, C, which is precisely the coupling that I've introduced here. Okay, so indeed the coupling here is capturing the class of the gerb, which is the target space of this signal. Okay, does that align, Justin, with what you were saying? Okay, good. Okay. Very good. So what about the symmetries? Well, the nice thing about this is that all of those symmetries I talked about, including the higher ones, now act in a natural way by automorphisms of this stack, of this gerb. So how does that work? Well, you've got the zero form symmetry, PSUN. That acts in a standard way on the base, on the coarse moduli space, just by Kähler isometries. That's a standard thing. And then the one form symmetry, BZQ, that acts on the fibers of this morphism. Okay, there's a natural action of BZQ on itself that's going on here. Moreover, you can think about the Postnikov class geometrically as well. This gerb structure is a notion of it being equivariant with respect to symmetries on the underlying space. And what the Postnikov class is doing is it's basically an obstruction, the last obstruction, to giving a PSUN equivariant structure on that gerb. So it can always be made SUN equivariant, but if you want to make it PSUN equivariant, there's an obstruction, which is precisely the Postnikov class of this two group. So in other words, all of the symmetries can be studied in this from this stack. I'm not saying it today, but these symmetries have various 't Hooft anomalies, and all of those 't Hooft anomalies can also be seen from the symmetries of this stack, but from this geometric picture, by studying line bundles on it and whether they can be made equivariant or not. Okay. So in a way, the kind of mantra is that in the same way that a moduli space, if you move out to a point on the moduli space, it captures spontaneous symmetry breaking. You break to the stabilizer group of a point. The stack is capturing spontaneous symmetry breaking of higher form symmetries. Those always lead to discrete gauge fields. All right, let me try to make contact a little bit with the picture of Wilson lines that I wrote earlier, because it really just translates backwards and forwards. So I'm really just doing a translation between the two pictures. They're the same. So the Wilson lines, WN, you can think about as line bundles on the weighted projective stack or the gerb. And if you recall, not all of the Wilson lines could end, right? That was what signaled the one form symmetry. Well, that's just the statement that some of these line bundles are fractional. So in particular, the local operators on which the Wilson line can end are sections of the associated line bundle. But on a stack, on a gerb here, some of the line bundles are fractional. They don't have sections unless n is a multiple of q. Or to put another way, they don't pull back from a line bundle on the base, on projective space, unless n is a multiple of q. And moreover, they only admit a PSUN equivariant structure if n is a multiple of q times n. That was the second property that the Wilson lines had. So all of this story about Wilson lines, what they can end on, it just has a direct translation into geometry here. And that's a nice thing to have. All right. So that's what I want to say about stacks. So maybe I'll just see if there are some questions before I move on. Okay, very good. So I now want to make some connections to K-theory, quantum K-theory, or really quasi-map K-theory, because I'm talking about a gauge theory. So let me first do the standard thing. So I want to think about compactifying my theory now in a circle. And then I want to try and get an effective two-dimensional description. So the idea is that we introduce mass parameters for symmetries and we integrate out the chiral multiplets. And then we try to get an effective theory for the remaining vector multiplets in 2 dimensions. And there's a very beautiful and old story here that I forgot to put the citations for, but the type of effective theory you get for the vector multiplet is completely fixed by what's called the twisted effective superpotential, a single function. It's determined at one loop, so it's explicitly computable in any gauge theory. And then you can think about the vacua that the theory has, or the vacua of the theory in 2 dimensions as solutions to this type of equation here. All right. So that's an old story. It has many connections here to integrability. This won't matter too much because I'm going to quickly translate it back into statements about Wilson lines and line operators. So let me just tell you what these equations look like for my example. Well, they look like the following. And all of the parameters here, P, X, I, Q, you can think about them as line defects wrapping this circle that I've introduced. So just to make a connection there, you might be able to view them like local operators in an effective 2D description. And then we're talking about a twisted chiral ring in 2 dimensions. But because they're coming from lines wrapping a circle, these are really line operators. Okay, so what are the objects here? Well, there's a dynamical Wilson line. So I changed notation here a bit. That's what I'm going to call P, but that's basically W1 in the previous notation. But I can also introduce background Wilson lines for any zero form flavor symmetries that I have. So these are almost trivial. In the absence of background fields, they're trivial, but turning on background fields, they're meaningful. And so in particular, Q is a background Wilson line for the topological symmetry, and the X's are background Wilson lines for the flavor symmetry. I'll make that slightly more precise in a second. And the equations kind of take an interesting form. In particular, if you stare at it a bit, you can convince yourself that the number of solutions is Q squared times N. That's good because that's in agreement with the Witten index of this theory, which you can compute from 3-dimensional gauge theory as well. And you might wonder whether this Q squared or this Q squared times N has anything to do with the symmetries that you have and whether it can be understood from a symmetry-based argument. But okay, so this might be a bit unfamiliar, so let me give a trick to think about it. So you might be more familiar with the case where I just take ordinary super QED, where I take the charges of the chiral multiplets to be 1, and then the ring relations take this form. It's basically the quantum K theory of complex projective space. So you can start with this form here, which might be more familiar, and then you can gauge a subgroup ZQ of the topological symmetry. And that's actually equivalent to just multiplying all the charges of the chiral multiplets by Q. So it ought to bring us back to the theory that I want. And this is implemented in this context by this type of transformation. This is a bit subtle, but you send P and Q to this combination here. And if you substitute this back in and close your eyes slightly, then you'll recover the result that you want. So this is not nothing too fancy. Okay. All right. It's useful again to think about this structure group. The structure group kind of dictates much of what's going on here. So as I said, the variables are Wilson lines for symmetries. So more correctly, what's going on here is that P is a Wilson line for the dynamical Wilson line for the gauge group. That's the E1 factor. The X sub J's are background Wilson lines for SUN, which is the universal cover of the flavor group. If you recall, I said that their product had to be 1 here, so they lie in SUN. And then the denominator here in the structure group that acts on these variables in the following way. And you can convince yourself that the particular combinations that appear in the vacuum equations are invariant under this transformation. And so what that means is that all of the combinations that you have are precisely the Wilson lines for the structure group S. And that's correct, because that's precisely what the structure group is. It's the most general group for which you can turn on bundles for your theory. Okay. So good. That's just to clarify a bit the structure of the variables that you have in the game. Okay. So the question I want to ask is there a kind of symmetry-based argument for this kind of degeneracy for the number of solutions? Well, the factor of n is fairly easy to understand. The Weyl group of SUN acts on the solutions, giving you a factor of n. What about the q squared? Well, you might expect the q squared has something to do with the one-form symmetry, and it does. The one-form symmetry kind of implies that there are two actions of ZQ on the solutions coming from shifting P and Q by a phase. So the first shift on P, that just comes from, again, staring at the structure group. There is a subgroup ZQ, which is the one-form symmetry, just rotates P. And then there's a second action as well, which is, I'm not going to explain too much detail here, but again, it's a consequence of the one-form symmetry, and it arises because there are fractional gauge vortices, or if you like, from this gauging picture, there are discrete Wilson lines when you gauge the ZQ. These are actually the generators of the one-form symmetry, the topological defects that generate it. And you can always multiply with those, and that gives this action here. So you kind of have two actions on solutions. That gives you a q squared. And so that gives you a kind of a symmetry-based argument or explanation of the degeneracy. But that symmetry-based argument requires studying the higher form or higher group symmetries to understand. All right. So if that was a bit mysterious, I'm going to give hopefully a clearer explanation of that, of a more general result in just a second. All right, but let me first say something about the mathematical interpretation. So what are these vacuum equations? Well, there are lots of kind of nice ways to think about them. It was kind of suggestive, the way I wrote P and Q, that you should think about those as position and momenta. And so indeed, there's a natural symplectic form built out of P and Q. And you can think about these equations as describing a family of Lagrangians for that symplectic form. This is where the connection to integrability jumps off. And in the same vein, these relations are exactly the relations in equivariant quasi-map K-theory of this weighted projective stack.
Sorry, Matt?
Yeah.
Do you mean T star C star or C star times C star?
T star,
like
C star.
You've got two logs?
Oh, sorry, it's a mistake. Yeah. Thanks, Justin. It's C star times C star. My bad. Yeah. Thanks a lot. All right. So again, there are lots of references here, so I do apologize for that. All right. So what's going on? Let me try to give a more refined answer, or why is equivariant quasi-map K-theory, equivariant quantum K-theory arising here? So one way to understand it is to put the theory not just in flat space and study its vacua, but study instead partition functions. So in particular, if you put the theory on a Riemann surface of genus G times a circle and ask what's the partition function, well, on the one hand, you can think about that as a trace over states in the theory on the Riemann surface. And it turns out that that can be written as a sum over solutions P star to these equations. So there are Q squared times N solutions of some function that depends on P and also Q and Xj. So I won't really tell you what that is, but it can be expressed in this way. But this partition function can also be expressed as an index. It's something that is, it's counting quasi-maps or vortices on the Riemann surface into this target space X. So it's really counting vortices in the actual theory that you have. If you want to think about it mathematically, you're studying quasi-maps into this weighted projective stack. So there's a moduli space of such quasi-maps, and you can compute its index, and you take a weighted generating function where the degree of the quasi-map or the vortex number is counted by the parameter Q. And that can be expressed as a sum over solutions to these equations. So this is very similar to the kind of construction of Telemann and Woodward and others where you compute the index of moduli spaces of G bundles. But here it's applied to quasi-maps. Okay. So the form of that partition function is very nice. There's always a factor of Q to the 2G out the front, where G is the genus of the Riemann surface. And then there's some rational function of the remaining variables, if you sum it up. So in particular, all right, so in particular, if G is 1, there's a Q squared out the front here. That reproduces the previous degeneracy. But otherwise, there's a more general result here. And a nice way to see that is that there are certain topological lines that generate this ZQ1 form symmetry, and you can just wrap them on 1 cycles on the Riemann surface. And whenever you do that, you're going to get a new state. And so again, this is a symmetry-based argument for this degeneracy of the Hilbert space in the presence of a 1-form symmetry in this theory. Okay. All right, so I can see that I've got 5 minutes left, so maybe I'll pause for questions. Yep, I can see that I should finish up quickly.
It was actually 50 minutes plus 10, but we've had a lot of questions, so if you could wrap up, I think that would be good.
I'll wrap up, yeah. So, okay. I only have a few more slides, but let me just say in words. So what I tried to get across is that 1-form and higher group symmetries play at least some role here in quantum K theory of Deligne-Mumford stacks. You can see it in the degeneracy that I've talked about. So you might ask if there's a more systematic understanding of that. Where is it coming from? Well, 2 groups are really categorical objects, and they, in the same way that groups act by automorphisms of vector spaces, 2 groups act by automorphisms of categories. So it's natural to try to find a category on which the 2 group acts. And the very rough idea that you want to do for that is you want to think about quantum K theory of your target space X. You might like to think about that as the ordinary K theory of the loop space of X in some way, and then pass from K theory to coherent sheaves on the loop space. And then the claim is that the 2 group will naturally act by automorphisms of that category. All right, and if you want to hear about how to do that, at least concretely, at least in these examples, I'll be very happy to talk about it afterwards, but thanks a lot.